Okay, good afternoon all. In previous lecture, we have completed surface heat treatment processes by changing their compositions. In that, we have studied carburizing, then nitriding and carbonitriding. We have studied these processes along with their procedure, their different types, and their applications. Now, there are two methods of surface heat treatment in which we are increasing the surface hardness of that steel material without changing their composition. Okay, and there are two types: flame hardening and induction hardening. These two types we are going to discuss in today's lecture, along with their subtypes. If any subtype is there, that we are going to discuss in this lecture. So we will start with the flame hardening. Okay, now here I have mentioned what is the how the process is conducted. This flame hardening process is conducted. You can read it, just read it. After reading it, I will move towards the next slide. There I have taken one diagram. With the help of that diagram, I will explain this concept. Now, what is the flame hardening here? Very much similar to other heat treatment processes. It consists of heating cycle, then some holding time, and after that it will we are going to cool it. Okay, in this process, in the flame hardening process, we are heating the surface layers of the steel material. Now here you have to choose the hardenable steel material, means which can be hardened. You cannot take low carbon steels here. You have to take either medium carbon steel or high carbon steel, or some alloy steels you can take here. That is a very basic condition. A hardenable steel you have to take, and you have to heat the surface layers of that hardenable steel with the help of a oxyacetylene flame, and you have to heat it above its upper critical temperature. Above upper critical temperature means you have to heat it above A3 for hypoeutectoid steels, or above ACM temperature for hypereutectoid steel. Depending on the type of the steel, you can choose the temperature range, and that temperature you have to achieve with the help of oxyacetylene flame. And after heating it, you have to uh, very minimum holding time will be there, and after that you have to cool that steel component with the help of the water medium. Now here you can do the cooling by just spraying the water on that surface of the steel, or you can directly take the steel component and you can directly do the immersion method. Immersion is nothing but directly taking the component and dipping that component into the water. And due to this cooling or due to this quenching method, what will happen? The austenite will get transformed to the martensite. Okay, due to this heating of the steel material above upper critical temperature, phase will be austenite, and due to the cooling with the help of water, uh, by spraying method or by directly immersion method, that austenite will get transformed to the martensite. Okay, now I will explain this concept. The principle of this hardening is explained here with the help of a diagram. Here you can clearly see that this is your job, or you can say that this is your workpiece. Okay, this is your workpiece, or you can you can go observe any one diagram you can choose, or you can simultaneously observe both the diagrams. Here this is your workpiece. This is hardenable steel. Here this is the workpiece, and now this is your oxyacetylene flame. Okay, oxyacetylene flame means with the help of that torch we are going to heat it. First we are going to heat it, means this is the hardened surface. Hardened surface means you have heated it with the help of this torch, and after heating you have quenched it with the help of water. Okay, first you are going to heat it, then after heating, uh, with the help of the water, just you have to spray that water on that surface and you will get the hardened surface. Okay, this is the concept here. Same concept mentioned here, and here I have mentioned one arrow. This is the motion, means from the this is the motion of torch and water spray from right to the left direction it is moving, means we have started from this point. Okay, flame will initially flame will be at this point. You will heat this point, and after the heating this point, the torch will move in the left direction, from right to the left direction, and simultaneously along with the heating you are doing the cooling operation. Okay, this is the cooling spray or water spray you are using here. After heating that component, just you have to spray that water on the surface, and it will get hardened. This surface is these are the hardened layers. Okay, so this is the principle of the flame hardening. Okay, it consists of your workpiece or job. Here one mistake is there in this diagram. Okay, I will explain it. And this is, instead of lower critical temperature, you have to hit it above upper critical temperature. Okay, this is above upper critical temperature. This is not lower critical temperature. Upper critical temperature should be there. And now this flame hardening basically consists of workpiece, then your oxyacetylene flame, and this water spray or source of your water. Now, depending on their state, you can say that whether they are fixed or whether they are in the moving condition. Depending on that, this flame hardening process is classified in four types. Okay, these flame hardening processes are classified in four types that I have mentioned here. First is the spot flame hardening, then progressive flame hardening, then spinning flame hardening, and combination of this progressive spinning flame hardening. Okay, I will explain it one by one. Now, in the spot flame hardening, what will happen? You are not going to means whole throughout the hardening will be not like this throughout. Just one specific spot will be selected. Okay, whether I will check whether that diagram I am having with me. Not having the diagram. Okay. Now, in this spot flame hardening, what will happen? Okay, in spot flame hardening, we will, from this workpiece we will identify one specific spot, and that specific spot is heated with the oxyacetylene flame above upper critical temperature, and after that the torch is removed, and that specific spot is cooled with the water spray. Okay, that specific spot is cooled with the water spray. That type of hardening or flame hardening will be termed as spot flame hardening. Okay, we are performing flame hardening, but we are going to choose a specific spot. Okay. Suppose only this spot you can select, any spot you can select. Suppose this is your specific spot, you can identify one specific spot, and that specific spot is heated with this flame, oxyacetylene flame, above upper critical temperature, and it is cooled with the help of water. Okay, and that specific spot will get hardened. That is the spot flame hardening. Then the second type here is progressive flame hardening. Now, in the progressive flame hardening, I have a diagram with two diagrams are there. Okay, this is your progressive flame hardening. This is progressive flame hardening. Here, this is your job, or you can say that this is the workpiece, and there will be means a torch will be there, or you can say that this is the hardening torch, progressive hardening torch. It will be like this. From it will consist of the two sources. One source will provide the heating. This will be the heating, and from another spot there will be some holes will be there, which will provide you the water. And in this progressive, these two diagrams are same. There will be okay, one torch will be there, and it will have oxyacetylene flame. Along with that flame, it is attached with the source of the water, or you can say that the source of the coolant. Now, from this right direction, from this side, your direction will be from right to the left. Okay, we are moving from this side to the this side. This is your flame. First we are going to heat it, then after that spraying will be there, and here your workpiece will be fixed. workpiece is in the fixed position, and the source of the heating and cooling, it will move, or it will be in the progressive, or it will be in the progressive state. It will move over the workpiece from one corner to the another corner where you are going to perform the hardening process. This is the progressive flame hardening. In the progressive flame hardening, workpiece is fixed, and heating source and cooling source will be in the moving state or moving condition. They will move simultaneously from one corner to the another corner. Suppose from this point we have simultaneously heating and cooling. Simultaneously, with the help of coolant, that area will get cooled, and accordingly we will get the hardened zone. Okay, in the progressive flame hardening, what are the main points here? Job or workpiece is fixed, and your heating source and cooling source are in the moving state. Okay, job is stationary, and they are movable, and they are moving on the that whichever workpiece is there, you are going to harden it, they will move on that. Whichever desired hardened surface is there, over that they will move simultaneously. Simultaneously heating and cooling or quenching with the help of water is done. Okay, this is the progressive flame hardening. Now the third type is the spinning flame hardening. In that spinning flame hardening, what will happen? That separate diagram I have not added here. Just you have to understand that in the spinning flame hardening, your heating source your heating source is fixed. Okay, please understand this. Your heating source and cooling source is fixed, and your workpiece will be in the moving condition. Okay, it will move, or it will be in the spinning condition. It will rotate. So you can understand that here the fourth type I have taken, that is the combination. Okay, I will explain that in this diagram here only. This is diagram for progressive and spinning flame hardening. Then I will explain it with the spinning hardening will be like this. The workpiece will be in the rotating condition, and whichever heating source and your cooling source is there, or cooling medium is there, they will be in the fixed condition. Okay, these are fixed, and your workpiece will be in the rotating condition, and it will get heated, and after that it will get cooled. Okay, simultaneously it will get cooled. It will be in the rotating condition. Exactly reverse of this progressive flame hardening. These two sources will be fixed, and this workpiece will move from one direction to the another direction, and in that heating and cooling will occur simultaneously, and it will get hardened. Now the fourth type is the progressive spinning. Now in this progressive spinning, workpiece will be in the rotating condition, and the heating source and the cooling source will be moving from one corner, or one end to the another end, and simultaneously heating and cooling will occur. Okay, it will move from this spot to the this spot, and it will be workpiece will be in the rotating condition. Okay, heating will start from here, and simultaneously cooling will be done, and it will get hardened. Okay, in this way these are the four types of this flame hardening, and depending on the condition of or nature of their workpiece and heating source and cooling source, four types are there: spot flame hardening, progressive flame hardening, spinning flame hardening, and progressive spinning flame hardening. I will explain it again. In the spot flame hardening, a specific spot is heated with the oxyacetylene flame, and it is cooled with the help of water by using the water spray. Then in progressive flame hardening, your workpiece is in fixed condition, and your heating source and cooling source will simultaneously move from one end to the another end, and hardening is done. In the spinning flame hardening, here workpiece is in the moving condition, or it will be in the rotating condition, and your heating source and the cooling source will be in the fixed state. Heating and cooling source will be in the fixed state, and workpiece is movable here, or in the spinning condition or rotating condition. And progressive spinning flame hardening is combination of these two processes. That is, workpiece is also moving or it is in rotating condition, and your heating source and your cooling source simultaneously they will move from one end to the another end, and hardening will occur. Okay, surface hardening will take place here. And at the end, what will happen? Due to the heating, austenite will be formed above upper critical temperature. Austenite will be there, and due to cooling, that austenite will get transformed to the martensite. Martensite will be present on the surface. Due to that, it will provide you increased hardness and wear resistance. So this is the concept related to the flame hardening, its different types. Then I will explain here some points, important points I have highlighted here. That is the what are the factors. There are certain factors. Before going for this slide, if you are having any query related to the principle of flame hardening and its four different types, please ask me. If you are having any query, I will wait for 2 minutes. If you are having any query or any questions, you can ask me. Try to understand that concept with the help of these diagrams. Put that in the chat box. If you are having any query, mention that in the chat box. Or if you are having, if all points are clear, also put that in the chat box so that I will move towards the next slide. Please mention reply. There some reply is needed. All points are clear. mm, Last few students. Padge is there, Pritam Padge. Pritam Padge, are you there? Then Sunil, roll number 62. Sunil, are you there? Nobody is giving reply. Sunil, roll number 62. Praveen, roll number 65.
Yes, sir.
Okay. Have you understood the concept of flame hardening?
Yes, sir. Yes.
Okay, okay. Okay. Okay, we will move towards next slide then. Okay, here some points I have highlighted here. That is on which factor, whichever depth of hardening we are able to obtain here. On this is, you are seeing it in the spot. This will be your depth of hardening. Okay, or hardened layers depth. This is the depth of hardening. How much depth of hardening can be obtained with help of this process, and on which factor it depends. Now this depth of hardening depends on several factors here. That is the distance between gas flame and the component surface. Then whichever gas pressures and ratios we are using in the that oxyacetylene flame. Then the, suppose the progressive flame hardening is there, or spinning flame hardening is there. Then what is the speed of travel of that flame, or speed of travel of the component. Okay, on that factors, that depth of hardening depends. And the fourth and very important point is the which type of medium you are using for quenching. Means type of the medium, then how much quantity or volume you are using of that medium, and how you are going to apply it, whether you are applying it by spraying method or you are using the immersion method. Depending on that, depth of hardened layer will change. Okay, now another important point is here that after performing the flame hardening, at the end of the flame hardening, as we are using very heating the component above 8 upper critical temperature, that is your A3 or ACM, it will be above 900 degrees Celsius. Okay, it will be above 900 degrees Celsius, and we are directly quenching it in the with the help of water. Due to that, what will happen, there will be some internal stresses will get created in the component. And if you used that same component which is having internal stresses in it in your actual use, then during its practical use it will get failed, or some cracks will get created due to the internal stresses present in that component. So to relieve these internal stresses present in that component, you have to do low temperature tempering process. Okay, low temperature tempering process, so that these internal stresses will get eliminated. Low temperature tempering means you have to heat that component in a temperature zone of 150 to 200 degrees Celsius, or in general you can say that 100 to 200 degrees Celsius, and you have to hold that component there for 1 hour to 2 hour, and after that you have to do the cooling. Okay, you have to do the cooling. Due to this process, what will happen, whichever internal stresses are there, that will get eliminated. Okay, in this way, means after flame hardening, low temperature tempering is performed to eliminate the internal stresses. Okay, and then related to the application point of view, generally this flame hardening is performed on the medium carbon steels containing zero point 0.4 to 0.7% carbon, or you can go for the high carbon steels also. Generally these are most suitable range of the plain carbon steel is steels containing zero point 0.4 to 0.7% carbon. Now this flame hardening is having some advantages. This process is having certain advantages and some disadvantages also, that I have highlighted here. You can see that in the next slide. I will show you these are the some advantages. That advantages are just I have taken it from whichever process we are using. Depending on that only, and these are the advantages. Here the distortion will be very less. Distortion in the component, it will be very less. Then, as here we have used the oxyacetylene flame, rate of heating is very high. Rate of heating is very fast. Means we are rapidly heating it. Due to that, what will happen? Oxidation and decarbonization is minimum or negligible. Then the cleanliness of working condition is very high here. Then very low consumption of energy will occur here. Very low consumption of energy will take place. And at the end of this process, we does not require any finishing operation or any grinding operation. Sometimes in almost all components, any means there is no need of further grinding or final finishing operations. Sometimes it may require that you can perform depending on the components shape and size. Then what are the disadvantages of this process, flame hardening process? Now this process, whenever irregular shaped component is there, you cannot do the flame hardening process. These are not suitable. You can do it, but proper hardening is not achieved. Means you have to take that oxyacetylene flame on that spot. If suppose irregular shape or complicated shape component is there, then that heating will not be proper, and at the end of that cooling process or quenching process, you will not get the desired hardness and wear resistance properties. That will be the disadvantage, and this process is little bit costly. That's why it is not suitable for the small scale production. Okay, so these are certain disadvantages and advantages of this process, flame hardening processes. Now, after this, we will see some applications. For flame hardening process is used for doing the hardening of these different components are there, that lathe bed guideways, then gear teeth, then you can say spindles, then shafts, mill rolls, then different kinds of the pulleys are there, that different kinds of the shafts are there. All these can be hardened, their surface can be hardened with the help of this flame hardening process only. Okay, so in this way this flame hardening process is completed. We will move towards the next type of surface heat treatment process without changing the composition of the surface, and that next type is the induction hardening. Okay, induction hardening is there. Whether that points are visible.
Yes, sir.
Okay, we will continue then. Okay, these points I have highlighted for your reference while you are studying it. Just I will explain these all these points with the help of diagram only. Okay, you have to draw the diagram compulsory. You have to draw the diagram. This will be the diagram in your VD code garage books. These diagrams are not available for flame hardening as well as for induction hardening. Diagrams are not available in your VD code garage book. So that please go through these presentations. You can draw these diagrams. Okay, then this is the diagram or arrangement, you can say that, for the induction hardening here. Now it consists of, here a high frequency generator is there. Okay, high frequency generator. From this we are going to get the means from high frequency alternating current is passed through, or how it is used I will explain it. Before that I will explain the arrangements. High frequency generator will be there, then this is your workpiece or this is the job. Okay, workpiece on which we are going to do the hardening of that surface. Then it consists of inductor coils will be there, and in that inductor coils, these are the inductor coils will be there, and cooling medium will be provided there. Now what will happen here, high frequency alternating current will be provided to this inductor coils, and due to that high frequency alternating current, what will happen, magnetic field is generated. Okay, through this inductor coils high frequency alternating current will flow. Due to that magnetic field will be generated. Okay, this in this way magnetic field is generated, and due to this magnetic field what will happen here, ed currents will get induced. Okay, magnetic field, or you can say that electromagnetic field is there, and ed currents are generated, and that ed currents will flow through the layers of this surface of your steel component. Okay, and due to the skin effect, one by one layer will get heated. Okay, how it is occurring, that I have taken in this diagram. Okay, this is the induction heating, how the heating will occur. So this is the heating process. Here you are able to see the current in the coil. This is the coil, and this is your workpiece. This blue color is your workpiece. This is the current in the coil, high frequency alternating current, and due to this high frequency alternating current, magnetic field, it will get developed. Electromagnetic field is created here, and due to this electromagnetic field, ED currents are generated and they flow through the workpiece, and they will heat the layer by layer of that workpiece due to the skin effect. Due to the skin effect, layer by layers get heated, and you are heating it above upper critical temperature of that steel component. Either it will be above A3 or ACM, and after that heating, this heating process will get completed within 2 to 5 minutes. And after that, with the help of this coolant, here some copper tubes are there and coolant is flowing through it. That cooling of that component will occur and that surface will get hardened. So this is the concept of induction hardening and how it is occurring. This induction hardening process that I have explained here. Now, very important points or some parameters I have highlighted here. The frequency used for uh, that alternating current will be 1000 hertz to 1 lakh hertz. Then time required for heating or that holding time is 2 to 5 minutes. Then whichever depth of hardening is obtained here, it will be from 0.5 millimeter to 6 millimeter. And after performing the induction hardening, very much similar to the flame hardening, it requires a low temperature tempering process to eliminate the internal stresses, and this low temperature tempering is performed at 160 degrees celsius to 200 degrees celsius temperature zone. Okay, so this is the induction hardening. This is its schematic representation, how the procedure is conducted or process is conducted, that I have explained. And important points in that, very important points are time required. First will be your high frequency. Frequency used will be in the range 1000 hertz to 1 lakh hertz, and time taken or time required will be very small, 2 minutes to 5 minutes. And depth of hardening achieved is a very thin depth can be also achieved from 0.5 millimeter up to 6 millimeter depth can be achieved with the help of this induction hardening process. So this is the principle of induction hardening process and some important parameters. Then that this heating concept I have explained. Now certain advantages and disadvantages are there in this induction hardening process. Now you will find some common points. Common points are there for advantages and disadvantages between flame hardening and induction hardening. So just I will repeat it. Induction hardening process is very fast heating process. It requires very less time, okay, as compared to other process till now whichever we have studied, from that carburizing nitriding, carbonitriding, flame hardening, and this induction hardening. Induction hardening requires lesser time. This is very due to very fast heating, it requires lesser time. No holding time is there, that's why production rate is very high. Then less distortions. Then oxidation is not there, oxidation decarburization is not there. Then we can control very easily, you can control the depth of hardening by changing the frequency and by frequency of that supply. Okay, you can change the alternating currents frequency, and by changing that you can control the depth of hardening very easily. This is the induction hardening. Then these are the common points for the flame hardening and induction hardening. That is the cleanliness of working condition, then very low consumption of energy as compared to other process, and only a light final grinding operation will be required, and in some cases it is not required also. Okay, so these are the advantages, as this is it is very fast heating, uh, and no holding time. Production rate will be very high. Then less distortion is there as compared to other hardening processes. And no scaling, no oxidation is there, no decarburization is there. Then you can control the depth of hardening very easily. And cleanliness is very at very high level. Then low consumption of energy, and very uh, light grinding operation or finishing operations are required. These are the advantages of this induction hardening process. Then disadvantages are very much similar to the flame hardening. If irregular shaped component is there, it is not suitable for. Okay, I have by mistake and I have written here flame hardening. Okay. This is induction hardening. This is induction hardening. This if irregular shaped component is there or complicated shaped component is there, it is very difficult to perform induction hardening because heating becomes difficult or heating will become non-uniform. Due to that, we will be not able to get the desired hardness or desired wear resistance of that surface. And as this process, which whenever you are reducing time, automatically it takes little bit cost. That's why it is only suitable for you can use for mass production, small scale production. You cannot this will be not economical for that. Okay, so these are certain disadvantages of this process. Then some applications I have highlighted here. You can do the hardening of crankshafts, axles, gears, camshafts, then rolls of the rolling mills, boring bars, brake drums. Then overhead traveling crane wheels are there for doing the hardening of their surface to improve their hardness and wear resistance. We are using this induction hardening. Some I have highlighted the list of the components here. Some names are common from the previous slides. Okay, gears, axles, camshaft, crankshafts, then spindles, pinions, piston rods, spur gears, pins, worm wheels, spur gears. Okay, I have some names are I have repeated here. Then helical gears, spur gears, locking pins, and common names that easily you can remember: camshaft, crankshaft, axles, gears. You can write. Oh, three, four names application. It is sufficient. Okay, this is for your reference purpose. I have highlighted some steel components on which you can perform the hardening with the help of this induction hardening method. So in this way, in this lecture, today's lecture, we have completed this flame hardening and induction hardening part. Okay, along with its principle. First, we have studied the principle of flame hardening, then its different types. Then we have understood its advantages, disadvantages, then parameters or factors affecting the depth of hardening, and I will repeat it with the help of slides. And after that, we have studied the advantages, disadvantages, and some application. Okay, flame hardening. First, we studied the concept or principle of the flame hardening, its different types. Principle I have explained with the help of these diagrams. Then its different types and factors affecting the depth of that hardened layer. Then in case both cases in flame hardening and induction hardening, you have to perform low temperature tempering to eliminate the internal residual stresses. Okay. Then most suitable steels are containing 0.4 to 0.7% carbon. In case of induction hardening, most suitable steels will be steels containing 0.4 to 0.5% carbon. Okay, here 0.4 to 0.7% carbon. Then some advantages and disadvantages are there, and some applications. Okay, you will find some applications common between flame hardening and induction hardening. Different shafts, pulleys, these are common applications. Spindles, gear, it is some common applications are there. Advantages, disadvantages points is almost similar in both the cases, just that induction hardening is little bit more fast. Disadvantages are similar and you can write some common names. Then induction hardening also we have studied this principle with the help of this schematic representation of induction hardening. Then we try to understand how the induction heating occurs. Then after that we discussed related to the parameters which controls that depth of hardening, then some advantages and disadvantages, along with few applications. Okay, in this way, we have completed these two hardening surface heat treatment processes, and these are doing means we in these two methods we are performing the hardening, or we are increasing the hardness of the surface and wear resistance without changing its composition. Okay, now only one point is remained from this chapter, that is the what is the concept of the hardenability. And there is one I think that Jomini and quench test is there, that we are going to discuss in the next lecture. Only one lecture is required now. After that, this chapter will get finished, and almost 80% syllabus is over now. Okay, only two chapters are there, and togetherly that two chapters will take maximum 10 to 12 lectures will be required. Okay, if you are having any query related to this flame hardening and induction hardening, its principle, its types, then advantages, disadvantages, that you can ask me. Please ask me if you are having any query, or you can mention that in the chat box also. If you are having any query, please mention that in the chat box. I'm waiting for your replies. Kindly provide replies so that we'll move forward. Okay, clear. Okay, Milind Jagdari. Okay, okay. Okay, in today's lecture, we have completed the flame hardening and induction hardening, along with their principal types, and advantages, disadvantages, and applications. Okay, now then, thank you for attending this session. Thank you. I will stop here. Thank you.